Hey everyone, welcome back to Take You Forward. So today we will be solving the problem DP20. And what is the problem? The problem will be minimum coins. Yes. Now this problem is again a problem on the pattern of DP on subsequences that we have been doing. And if you remember DP on subsequences, it's very easy. Pick and non-pick is what you generally use to solve DP on subsequences. So it's a similar kind of problem. So what does the problem state? So the problem states that you're basically given an array which denotes denomination of coins. Assume the denomination of coins are 1, 2, 3. Like you have coins which have denominations as 1, 2, and 3. Okay. And you're given a target. Assume the target is given as 7. Okay. So what they're asking you is what is the minimum number of coins? Yes. What is the minimum number of coins that you will require in order to form this particular target? So over here, I can say if I take one coin of three denomination, another coin of three denomination, another coin of one denomination, that will add up to give us the given target. And how many number of coins did we use? The answer to that will be 3. So you have to minimize this number of coins. Like there can be other ways as well. You can take 2, you can take 2, 2, 2 thrice, and then you can take a 1. This also gives you a target, but over here the number of coins required is 4. I don't want that. The question clearly states you have to figure out the minimum number of coins required. Now you might be saying, Striver, this is very simple. We are just gonna take the target and whichever is the maximum value, we divide by it like greedy way. Like the first approach. So you'll be like, we can definitely solve this using greedy. So if it was greedy, it would have been like, okay, these are the array elements, and the target required is 7. Pick up the biggest coin, which is 3. Can I have it? Yes, it divides it by twice. So I can have two denominations of coin 3, right? And what is the leftover part? 7 minus 2 denomination of 3, which is 7 minus 6, leftover is 1. Which is the next biggest coin? 2. Can it divide? No, 0 denominations of 2. Which is the next biggest coin? 1. Can it divide? Yes, 1 denomination of 1. And after this, 1 minus 1 denomination of 1 will be 0 left. So you'll be like, okay, I'll require 2 coins here, 1 coin here, which sums up to give me 3 coins. Greedy does work for this test case, but it might fail. So can we figure a test case where greedy fails? Assume I give you something like 9, 6, 5, 1. Okay, and these are the denomination of coins, and I'm looking for a target of 11. Okay, I'm looking for a target of 11. So will this fail? If you apply greedy, the biggest coin is 9, and you'll be like 11 by 9, one denomination of 9, leftover is 2, 6 cannot be applied, 5 cannot be applied, 1 can be applied twice. So you'll be like, I'll be requiring 3 coins in order to form the target of 11. But actually, if you pick 6 and 5, the requirement of coins will be 2. And we saw that if we follow the greedy method, it does fail. Again, why? Same reason. Uniformity. There is no uniformity there, right? There's a 9, but it might happen the next couple of elements might be something which gives you better values. So uniformity is not there. Like if you 9 to 6 difference is 3, 6 to 5 difference is 1, 1 to 5 difference is 4. So there is no uniformity in the differences of coin. Thereby you don't know what is the next denomination. Hence, something like greedy cannot be applied in such cases. And that's when we think of what? Trying out all combos to form target. And this is something which we have done in which problem? Knapsack. Over there we had to figure out the maximum value. Over here we have to figure out what is the minimum count, right? So try out all the combos and take the combo that has minimum coins. Take the combo that has minimum coins, right? So the problem is to figure out minimum coins. So what is the rule? What is the standard rule to write the recurrence? And how do you try out all combos? There's only one way. That is if you write the recurrence or recursion, and then you can think of DP, tabulation, and everything. So rules Do you remember the rules, guys? I've been teaching that forever now. What are the rules? First rule is express the recurrence in terms of first is index, and obviously you're looking to form something. In the knapsack also you had a bag. Over here also you're looking for a target. So the second recurrence will be target, which I can call it as T, right? Then express, yes, then express. Third, you have to take the minimal of all, right? You have to take the minimal of all because over here the question clearly states find out how many minimum coins will you require. So what is the question stating? The question is stating to find out the minimum coins, correct? So can I say I have to write a function that returns the minimal coin? So if I'm writing n minus 1 and target, so that means if there is an array like this, yes, if there is an array like this, where this is 0 and this is n minus 1, I am saying till n minus 1, till the entire array, what are the minimum coins that will be required to form this target? This will tell me is it 2, is it 3, is it 4, is it 5? What are the minimum coins? This f will tell me. Whatever is the question, that is what the f generally resembles. So this f is going to tell me what are the minimum number of coins that you'll be requiring to form the target. And for this portion of the array, n minus 1 means the array ends over here. So I can say I can start easily. Okay, so let's write the recurrence now. So we have an index, okay, and we have a target. So let's forget about the base case. And what did we learn about this express all possibilities? Generally, in subsequences, there are two possibilities. Either you take the coin, or you do not take the coin. But over here, there will be slight difference. Let's understand why. So if you carefully see, whenever we took the coin 3, we used two additions of that, right? We used two additions of that. So the question states there is an infinite, yes, there is an infinite supply of coins. In the previous questions, a single element was just used once. Like in the knapsack, what you did was if you steal or stole whatever, an element, you just stole it once. But over here, this denomination can be used once, twice, thrice, as many times as possible, right? Now you might be thinking, Striver, then the best thing is divide it. Like if you're using it, do a 7 by 3. They're using it twice, take twice. Will that make sense? No, because it might happen. You don't need always like assume there is something like 25. 25 by 3 is 8 times. You don't need to use it 8 times. Probably there might be a case where you just have to take 7 denominations of 3, make it 21, and probably take 2 denominations and make it 25. There might be cases like this. It's always not necessary that if you're using a denomination, you end up using the entire portion. I will again repeat. Assume there was a target of 25 and the denomination is 3. It does not necessarily means that if you're taking the denomination of 3, you take 8 denominations of 3. It can be 7 denominations, it can be 6 denominations, it can be 5 denominations, it can be any number of denominations that you can. Make sense? So I'll be like, okay, there can be two cases. One is I decide I will not take. That's for sure. And if I not take, am I adding to the number of coins? Because the function, what is the duty of the function? To return the number of coins. So make sure when you're not taking, you count the number of coins. So the number of coins counted will be 0. And if you're not taking it, what happens to this f? You had an array, right? You probably are standing over here, and this is your portion. And if you do not take it, you have to move back. So please move back. So when you move back, it will be index minus 1 and target. Perfect. And what about take? So if you're taking, right? If you're taking, now you're looking for minimum. If you remember, I told you, whenever you're looking for maximum, assign everything to int mean so that it's not considered. Whenever you're looking for minimum, assign everything to int max so that it is not considered. So if you're taking it, make sure take is considered as int max. Okay, now when can you take it? So this array, you are at this index and assume this is 6 and the target is 3. Can you take this denomination? Will it make sense to take this denomination? The answer is no. Because if you take a denomination of 6, but you're looking for a target of 3, so it does not make sense. So before taking any denomination, just make sure you ask, does the coin at that index is lesser than the target that I'm looking for? If it is, then I can take it. Now, if you're taking a coin into your denomination, let's understand. If you're taking a coin, what is this function doing? This function is counting coins. This function is counting coins. So, how many coins are you taking? One, and rest for the remaining target you have to figure out, right? For the remaining target is t minus coins of index, because if you took up a coin, if this is the array and there was 3 and the target was 8, so if you took this 3, this 8 will reduce to 5 now. That's what I'm doing over here. This 8 will reduce to 5, and now you look for what are the minimum in which I can form this 5. That's why you'll again call this function choice. You will again call this function by taking it. But there's a question, what will happen to this index? Because if this 3 is picked only once, you add 1. But if you go back, you will not be allowed to pick it once more. So the best thing that you do is you say, I'm going to stand over here itself. Yes, I'm going to stand over here itself, and I'm going to pick it again. So I will call the index again, and this time with a reduced. So basically what I did was, if there was a 3 and the target was 8, so I was looking what are the minimum number of ways in which I can form 8 in this portion of the array. Now, if I picked up once, this will be 5, and I'll again look in this array. In how many ways can I form 5? That's my motive, that's my thinking. Make sense? So what I did was, I stayed at the same index. Remember this as a thumb rule. Whenever there is an infinite supply of anything, infinite supply, multiple use, such statements, whenever there is infinite supply, multiple use, such statements, always when you consider take, it will stand at the same index. It won't move to the previous index. It will stand at the same index. Now you might have a question, but Striver, if it stands at the same index, it will keep standing. No. First it was 8 when you picked up 3. Next it will become 5 when you pick up 3. Next this 5 will become 2. And then you cannot pick up this 3. Hence, ultimately you'll move. You will move at a moment, because by picking up, you're reducing this target, you're reducing the target as much as possible. So eventually you will move. So that's the funda of take. You always stand at the index. Remember this. Whenever there is something like infinite supply, something like multiple use, you always will stand at the same index, and you'll just alter the target. Yes, you'll just alter the target, whatever, like by how much possible you have to alter it. So that's what you have done. And now what do you need to return? The minimum of the combo of take or not take is what you have to return. So this is what you will do. You'll return the minimum of take and non-take. So have I written the recurrence? Express recurrence minimum of all. What is the next thing? The next thing is base case, and I've already taught you that. How do you write base cases? Whenever there is a case of base case and you're starting at n minus 1, you always look at the last index, which is 0, and then you start thinking in terms of a single array containing a single element and a possible target. So this is an array at index 0 and possibly containing a value 6 and a target 7. Now tell me one thing, if this is containing a value 6 and a target 7, can this target be achieved? Like, what are the minimum number of coins? If I ask you, what are the minimum number of coins that you will take to achieve this target equal to 7 is my question. What are the minimum number of coins that you will take in order to achieve this target 7? And your answer to that will be, Striver, the answer will be 0, because I cannot achieve the target 7 using a coin denomination of 6. But what if I tell you that this is 7? Now your answer will be, Striver, we can achieve it, because it will take us one denomination of 7 to achieve this target 7. Now let me quickly change something. If I change the target to be probably, let's say, 12, and the over here it's 4, then you'll be like, Striver, we will be requiring 3 denominations is the minimal that I will require in order to achieve this target via the denomination 4. So can I say, if the target is divisible by this 4, just very logical, if this target is divisible by this 4, then I return the minimum as target by denomination, right? And if it is not, then I'll return that it's not possible. So thereby the minimum number of coins is infinite. No matter how many coins you bring, you cannot, don't return 0, otherwise the minimum steps will be counted as 0. Don't return 0. So let's write down the base case. So the base case will be very simple. If index is equal to 0, and then you'll have to write something. So I know, and we are always assuming these cases, that the coins will always have a denomination of greater than 0, because there will never be a denomination of coins you like. That's common sense. So if array of I, or rather if target modulo array of I is equal to 0, we will return what? We'll return target by a of I, because that's the minimal that we will require. Or else there is, like, we cannot form it. We will return int max. That is how you can easily do this stuff, right? And just to make sure that it is no overflow, probably you can return something as 1e9. Again, why? Because see, you're adding 1 plus 1 plus, if any of the function gives int max, it will be 1e9. So, like, if any of the function basically gives, like, it's 1 plus 1 plus, any of the function gives int max, so int max plus 1 will go overflow. Thereby, in order to have safety, I'm returning 1e9. Okay, what's the next case? Let's take an example and try to draw the dry run on the recursion tree so that the stuff gets more clear to you. So let's take this example and do a dry run of the recursion tree so that you understand how this is working. So initially we are, like, if I just try to write, we are at f of 2 and you're looking to form 8. You can take, like, you cannot take, or you can take. So assume you do not take. You move to the previous index with the same target. But if you decide to take this guy, so 8 minus 3, the target will reduce to 5 now. And there will be a plus 1 of coin. So you still stay at the same index, but the target reduces to 5. Perfect. Now you are at f of 1, 8. You are saying, in this portion, can you form 8? Can you form 8? And over here what you'll do is you'll say not take and take. So if you not take, you'll move to 0 and you will be at 8. Correct? And over here if you take it, if you decide to take it, plus 1 coin, and if you take it, there is 2. There is 2. So eventually what happens is, you still stand at 1, but there is a reduction in the target that you're looking for, 6. At 0, 8, what happens? You are at this and you're looking for a target of 8. There'll be 8 coins required of denominations 1, right? So you return 8 coins. Perfect. This guy returns 8 coins. F of 1, 6 will again be not. So f of 0, 6. So at f of 0, 6, there'll be 6 denominations. Make sense? And if you take again 1, and if you take 2, it will be something like 6 minus 2 will be 4, and plus 1 over here. And f of 1, 4 will again be not take, which will be f of 0, 4, which will again return 4 denominations. And if you take it, it will be f of 1, 2. You see, every portion, like every combination is being checked out thoroughly. Now at 1, 2, what can you do? Again, you can not take, which will take it 0, 2, which will return 2 denominations. And f of 1, 0. Again, you can go across. And this is how it tends to work. Like, this is 0 denominations. 1 denomination of 2. Another denomination of 2. Another denomination of 2. Another denomination of 2. Like 4 denominations of 2 also make 8. Or 2 denominations of 2. 4 denominations of 1. Or 3 denominations of 2. 2 denominations of, like, every angle is being seen on this particular recursion tree. But what will be the time complexity of this recursion? You're Now over here, is it 2 to the power n? In all the other cases, it is, but over here it is way greater than, like, way greater than big of 2 to the power n, because for a particular index, you're taking it and you're still standing on the same index. So in order to analyze this, you have to say that for every index, the options that you have is not exactly 2 to the power n, it can go beyond that. Thereby we can, like, in general in the interview, you don't have to explain so much. You can call it as exponential, because you cannot theoretically prove the time complexity. So you can call it as exponential, saying that every time our recurrence picks up, it stands at the same index. So for an index, now we don't have two ways, there can be multiple ways, right? So there can be a lot of ways. The time complexity is exponential as of now. What about the space complexity? We're using an auxiliary space of big O of n. Can we say this again? No, it's way more than that. Why? Because if you are standing at the same index, and if you look at the recursion tree, because of the standing of the same index, the auxiliary space is not big of n, it can go beyond than that. So at max, it will be like, assuming the minimum coin denomination is 1, at max it can go up to big O of target, assuming it reduces by 1 1 1 1, it can go till target. So again, a very different problem in terms of time complexity and the space complexity. The next step will be to definitely memorize this. We can see that it's a very different problem. Like, it's not the typical problem where you can easily say 2 to the power n, big of n. Because of this particular standing on the current index, it tends to be far greater than the obvious problem. So what's the next step? Obviously memorization. And how do you memorize? If there are overlapping subproblems, so if you take bigger examples, there will be overlapping subproblems. And in order to memorize, you look at which parameters are changing. One is index, one is target. So whatever index is given to you n, and assuming the max target is target, you'll require this size DP array in order to have it memorized. So make sure you memorize it. And step is very simple. How do you memorize? If I go back, yeah, you basically write dp of index target equal to, and over here you write if dp of index target is not equal to -1, you return dp of index target. That's it. That's what you easily do it. Couple of steps and you can memorize any recursion into dynamic programming. Now the moment you memorize this, yes, the moment you memorize this, what is the time complexity now? We go of n into target, and the space complexity is now around big of n into t, but still the auxiliary space is around big of target, slightly beyond that. So this has to be still reduced. And how can you reduce it? Very simple. Tabulation is the way to go, yes. So what are the steps to tabulate? I've already told you that. It's very simple. First, base case. Second, look at the parameters that are changing. First parameter index, next parameter target, and write it in the opposite fashion. Third, copy. Copy the recurrence. You can convert any memorization into tabulation. It's a matter of seconds. So let's analyze the base case. So we have to declare a dp of n and target plus 1. That's for sure. So in order to analyze the base case, let's look at the base case actually. So what is the base case stating over here? It states if index is 0 and if the target is modulated of a of I, what can be the values of target? Always think, like, don't think this target as the initial target. It is not the initial target. When the index is 0, like, there might be a call for 0,6, there might be a call for 0,7, there might be a call for 0,8. It can be anything. It can be anything. So can I say the target can be anything from 0 to t? It can be anything from 0 to t. Make sense? So for anything from 0 to t, what does it have? T by a of I if it is getting divided. So why don't you write that? It's very simple to write. So go ahead and write it. For any target from 0 to the original target given to you, if the target is modulated of a of I is equal to 0, or I can probably write this in some other lines. If the target t modulated of a of 0 is equal to 0, I can say dp of 0 target is equal to a of, or rather target by a of 0. Else dp of 0 target will be int max. That's what you wrote. Simple. This is how the base case will be. As simple as that. Just look over there and try to copy paste. What about this? Your recursion runs from n minus 1 to 0. 0 is the base case. What's tabulation? Bottom up. Which is the bottom case? 1. So you start from 1 till n minus 1. What about target? You started from target till 0. Go in the opposite fashion. So it will be 0 till target. That's it. I think we're pretty much done. So next step is copy the recurrence. So I'll show you that in the code now. So you're basically given this minimum elements function and the array num and the target. Okay, so we can write the function. So let's start off to write the function int f, int index, int t, and really we can carry the vector as nums. Do you need anything else? I don't think. So I can say the base case is very simple. If index is equal to 0, if the target is more, let's quickly check out if all the array elements are greater than 1. Yeah, it is greater than 1. So if t modulated of a of 0 or nums of 0 rather is equal to 0, we can definitely return something as what to say, probably something as t divided by nums of 0. Make sense? Or else we will return something as 199. Again, not an int max, and there will be a not take case. Can I say the not take case will be very simple? 0 plus f of index minus 1, and the target still stays as the same, and the nums. And can I say the take case initially will be int of max because you're looking for, or rather you can just keep it as int max. Yeah, that's perfect. So what about the take case? I definitely can pick it if it is lesser than equal to target, and if I pick it there'll be 1 coin and will still stay at the same because we can reuse it, and the target reduces by nums of index, and I can just pass on the nums and it goes, and I can return the max of take and not take, and that should be fine. And we will be returning the answer as f of n minus 1, and obviously n is not given over here, so please make sure you can compute the m by taking nums, rather num dot size. Okay, perfect. And we can just pass on the target and the num array. I think it should be fine. Let's quickly run this off. So you're getting some wrong answers. It's because they've clearly stated if the answer is not possible, print -1. So what we need to make sure is, just make sure over here, if yes, just make sure over here, probably you can keep the answer as this, and then make sure if yes, if the answer is, because what are you returning? You're returning something as 1e9, right? So if by chance the answer goes somewhere beyond 1e9 as the number of steps, return -1, or else whatever is the answer stored, you can just directly return it, and then this should be fine now. As you can see, this is fine now, and if I submit this, this will definitely give TLE. Why am I submitting this? Now it's time to memorize this, so let's quickly try to memorize this. And in order to memorize this, I'll take a vector, a dp array, and a size n, and a vector another int, a target +1 and comma -1, and I can easily pass on the dp array over here. Let's call the dp array over here vector int and dp. Over here the dp will go, over here also the dp will go, and over here the dp will come across dp of index and t capital, and over here if dp of index t is not equal to -1, return dp of index and t, right? And we can just now quickly run this off and see if this is running fine. It is. Now let's quickly submit this. This is accepted, but as I said, the auxiliary space has to be removed, as I don't like memoization because of the extra auxiliary stack space. Time to convert this into, yeah, tabulation. First step, make it 0. Just make sure this is nums, because we're gonna copy paste and we have used nums over here. Enter. That's the first thing, base case. For int t equal to, I have already described this, 0 for every t lesser than target and t plus plus. What is it going to be? If the t is modulated by nums of index, that's 0, then dp of 0 of t will be the same thing that we have written over here. Else, if it is not, then dp of 0 and t will be 1e9, the same thing that we have written over here. If it is, then this, otherwise not written. What's the next thing? Changing parameters, index from 1 to n. Perfect. Next changing parameter, target from 0 to target. Quickly write it. What's the next thing? Copy paste. Just take it. Go over here. Copy paste this, the same thing. And just make sure instead of this, write this portion. And what you can do is just omit this, change it. Instead of this, write this, change this. Perfect, done. Instead of return, have this over here. Instead of f of n minus 1, make it dp of n minus 1 target and change this. I think we're pretty much done. Let me just quickly, yeah, looks like this is it. So if you do this, you're getting all the right answers, and let's see if this is correct. So this is giving time limit exceeded, partially accepted. Probably they would love you to space optimize this. So let's quickly do a space optimization on this. So as you know, you'll be requiring a previous of target plus 1 comma 0 and a current of target plus 1 comma 0. So why can you space optimize? Again, the same reason that I've been teaching in the last 19 lectures. Whenever you see something like index minus 1, it's just the previous row that you need. It's just the previous row. So please do it. First of all, this is what the previous will be. Because of the first row, dp of 0. First row is done. What about the next thing? Instead of dp of index minus 1, this is going to be previous. Instead of dp of index, this is going to be current. Instead of dp of index, this is going to be current. And right over here, it is previous equal to current. And what is over here? It can be previous or index or curve, whatever you feel like. So you just declare a couple of same column size, same number of columns, and then you just make sure that instead of computing in terms of dp, you just take it row wise and just transfer the code. So if you see, if I run this off, I think this should be running. Yeah. If I submit this, let's see if this passes all the test cases or not. It does. So the space optimization solution is passing all the test cases. The tabulation, memoization passed all. The tabulation did not. Not sure why. It's mostly because, I'll tell you the reason. A lot of times happens is you can design test cases in such a way. In memoization, you actually don't visit all the n into target states. So you might be visiting very less amount of states. Yeah, there is an auxiliary space, but you must be visiting a lot lesser number of states. But if you look over here, it exactly visits n into target states. All the states n into target states are visited over here. But that's the reason mostly. Sometimes it might happen, but most of the time it does not. So probably they have designed the test case in such a way. So guys, that will be it for this video. I hope you have understood this entire video. So just in case you did, please make sure you like this video. If you are new to the channel, please do consider subscribing. And to continue our tradition, please make sure you comment understood before leaving off this video. And yeah, with this, let's wrap up this video and meet in the next one. Till then, bye bye, take care.